Okay, this is part 2 of drawing motion diagrams. And after watching this video, you should be able to draw complete motion diagrams, including velocity vectors and acceleration vectors. Now I want to pick up here with an example that we left off with on part 1, which was something like this. A ball is rolled into a wind, it slows down and comes to a stop and then speeds up in the opposite direction. And I'm going to draw the dots for the motion diagram for this motion, starting here. So at time 0, there, and then there, and then there, and we put them closer together to show that it's slowing down. And maybe by that point it comes to a stop. And maybe it then turns around and comes back in the opposite direction. And so that's a motion diagram for that, but that doesn't include the velocity vectors and the acceleration vectors. So let's do those. I'm going to do those in a different color so it'll be more obvious. So the velocity vectors want to show how fast and in what direction. And so we're going to put an arrow sort of associated with each dot that shows the direction, and the length of that vector, as you know, shows the amount or the speed of the object. It's slowed down a little bit here, and then it's slowed down even more, and then it's slowed down even more, and there it's stopped, so we don't need a vector at all because its velocity is 0. At this point it's picked up speed but in the opposite direction. So our velocity vectors will be in the opposite direction, but growing in length as the wind speeds this ball up. All right. And yet a complete diagram will need also acceleration vectors. Now I'm going to do those in green, but also we're going to make the acceleration vectors double arrows. So an arrow like that is an acceleration vector, and an arrow like this we'll use to represent a velocity vector. All right, so let me go back to green. All right, so now in this one, in this situation, the ball is slowing down. That must mean we have to subtract meters per second of velocity from what it's going here. And so to indicate that sort of thing, we need an acceleration in this direction. Let's say this is 5 meters per second, this is 4, then the acceleration must be 1, but in the negative direction to get us from 5 down to 4 meters per second. As we are modeling objects with constant acceleration, we'll assume that acceleration hasn't changed there, and there, oops, and here. And again, we should draw all those the same length because the acceleration needs to be constant. And here also. You might think, hey, it stopped there. Well, sure it is, but it still is accelerating. If it wasn't, it wouldn't change its velocity at all, but it is now not stopped. So we have to again show its acceleration here. And again, constant acceleration. Here we need to show in the negative direction still so that we can go from like a negative 1 meter per second to a negative 2 meters per second, or whatever the numbers might be. Here again, and again the idea is to within a rough approximation, the acceleration vector is the same length. So there is a complete motion diagram that is a good way to visualize the motion of a ball rolling into the wind, slowing down, coming to a stop, and then speeding up as it goes in the opposite direction. This will be one of many kind of representations we're going to use to represent motion. And in class and other places, we'll see how a motion diagram can be related to a graph. That's all for this video.